is Nick Tabin. I'll be doing the XFLR5 video project. My group. So when you open XFLR5, it's going to look like this. You're going to go to Module, Direct Foil Design, and now we need to input our foil. So you're going to go to Foil, Naka Foils, the 2415. The number of panels is 250, and hit OK. So now we have our Naka 2415 ready, and so now we need to actually do some analysis. So now we're going to go to the X-Foil Direct Analysis under Module, and now that we're here, we're going to set up a batch analysis. So Analysis, Batch Analysis, and we're going to have a bunch of different Reynolds numbers. In here you can change and add as you like I'll just throw this one in here as an extra just to show. But now this is going to gather the data. So I put my max thread so that way it goes quicker. And for the actual wing analysis, we're going to be doing it between -5 and 25, but just so that way I can gather a bunch of data for the foil. It should help during the wing analysis. So I'm going to do it from -10 to 30. Just give myself some extra leeway there. And now we're going to analyze. Okay, now it's done. So the important thing here is the smooth curves are the ones we want to pay attention to. These ones that are going kind of crazy here are due to the fact that the airfoil has stalled, and so XFLR5 cannot necessarily extrapolate or interpolate that data very well. So we kind of want to make sure we focus more so on these nicer curves. Those are what's going to pertain more to what we're doing. So now that we've got our data, we're going to go to Modules, Wing and Plane Design, and now here we're actually going to set up our plane. So we're going to go to Plane, define a new plane, get rid of Fin, get rid of Elevator, and now we're going to define our main wing. So for our wing here, we're going to do an aspect ratio of 14 and a taper ratio of 0.5, with the root chord being 2 meters long. So we need to make sure we turn our offset to 0. This chord corresponds to this outer chord here, so this is going to be 1, because it's half of the root chord, and then the root chord here is 2. So there's that, and now the last thing we need to do is change our span in order to make sure that our aspect ratio is correct. So if you look and see, we have a nicely tapered wing here. The next step is to make sure that we actually input the foil as the plane itself, so that way we can get our actual foil, or our actual wing here. So now we have that. We can see we have an aspect ratio of 14, span, area, taper ratio, all those are correct, so we are good to start. So we're going to go save, and then save, and now we need to set up an analysis. So we're going to go to define an analysis. It's going to be a type 1 at 50 meters per second. It's going to be our free stream, LLT here, and then there's nothing else in here that we need to change. So we're going to go to save. And now over here on the right is where we're actually going to set up where we want it to, or the angles of attack rather, that we're going to have it analyze at. So it's -5 to 25 with increments of 1 degree. So now we're going to analyze, and we see it's converged all the way up to 20, and then 21 through 25 did not. This again is because of the fact that the wing itself is stalled, and so XFLR5 has a very hard time as to actually interpolate and converge or gather data at those values for different Reynolds numbers. Sometimes what you can do, and I'll just show it, but I won't do another analysis for this, is sometimes it'll work if you go into the actual airfoil and you add in this specific Mach number. So we're just going to copy that, close, and I will show it. Go back to direct analysis. We're going to go back here to analysis, batch analysis, and It was in the 3s, so we're just going to do an insert after here. And we're going to put that in. Go like that. So now we have that, and then you could analyze it again, and sometimes that will work. I'm not going to do it for this because we're purely here to show. So now we go back to the wing and plane design, and then we go over to our polar graphs. We're going to go and define this graph settings. It's going to be for alpha. And we see our CD induced, our CL over alpha, CL over CD. And you can change each one of these. You can change each one of these graphs to show you a specific thing. So we will do just for show. We'll just show a CD over alpha here. So we have our total CD over alpha here. And this, again, corresponds to our total CD. So now that we have all this, what we're going to do is export these results. We'll say AR14 TR0.5. And we'll leave this like so. And now we're going to go into the Excel. Upload a file. Open. So now we have we have most of the data that we're going to be using to solve. So just to give a quick show on how you're going to start doing the graphs, we're going to go to Insert. It's got to convert it into an Excel file. So we're going to insert. We're going to go to charts. And we're going to do a scatter with smooth lines here. We're going to select the data. So we're going to start here. And then here. We're going to apply. The X values are going to be our alpha values. Check, and then our Y values are going to be our CL values. And so now you can see we have a smooth curve of our CL with respect to alpha. So now what we're going to do, format the chart. It's got a title, it's got a legend. I'm going to rename this to AR14 TR0.5. We're going to leave it like so. And then we do need to add axis title here, and this is going to be our alpha. Same thing for our vertical axis. We're going to do an axis title, and this is going to be our CL. And there's how you do it for the first one. So now we're just basically going to do the exact same thing for the rest. So we'll do another scatter here. And this part, since we're doing it on the thing, doesn't matter so much. So now, series, edit, our X values again are going to be here. Y value, back that out. We'll use CD here. And then you would adjust the chart as shown before. In order to add the grid lines and adjust it how you need. So now the next So you would do that, you would repeat this for everything. So CL over CD versus angle of attack is all you're going to do would be, you're going to set up a formula, so it's going to be this divided by this equals, and then you just click and drag this all the way down, again divide by 0 because there's nothing in those, so we can just delete those out. And now we'll do this. And so again, we're just gonna do that just to start getting that going. Or rather, our X values are going to be this. Y values are going to be CL over CD, which is this. And now we can see our CL over CD versus angle of attack graph here. So again, you would do that for also the CL versus CD, which is just the CL is your Y, your CD is your X. And for multiple different plots having the airfoil and wing shapes and whatnot, you would just overlay all of these into one. And then determining and tabulating the lift curve slope from the CL versus angle of attack. All you're going to do, so this is our CL versus angle of attack, so we'll just do CL versus AOA. You're going to basically pick any point on this graph and then just do find the slope of it. So I would do between alpha 4 with this value, alpha 0 and this value, and then all it is equal sign your change in CL, so it's going to be this minus this divided by this minus this, and the parentheses are important. So this gives us our lift curve slope for the angle of for the CL versus angle attack of this wing here. It's important to note that this is going to be in degrees here because all this is in degrees. So you would convert it by multiplying it by pi and then or multiplying it by 180 and dividing by pi, and that'll give you the radian. So it'll be equal sign 14159 divided by 180 times this value, and so this is a corresponding in radians. Or I did that backwards. It's supposed to be the other way. It's supposed to be by 180 divided by, and so that's the corresponding radian value. And remember again that for a thin airfoil, it's the A naught is 2 pi or 0.11 per degree, and both of these are beneath that. So we are good there. It means that this is correct and actually usable data. So we've got that, and compare these with the theoretical. So again, I already just did that. The minimum CD and the corresponding. So you can just basically search through this, or you can just set up a little function to go equal sign min of this. That'll tell you that value, and then you just look specifically for that value, and we find it that it's at -2 degrees. So this corresponds to our -2 degrees. You do the same thing for finding the max CL, so you would go through equal sign max, and then find it at its highest alpha value, or at its corresponding alpha value. And then CL over CD again. So you just do another equal sign max of this column. And so these are in order. So all you would do is that, just to make it easier on yourself, you do max, and then you would find the max CL over CD value here. And then you just put that corresponding there. The zero lift drag coefficient of the CL versus CD graph is basically you take this, and then you find where there's zero lift, which would be right about here. And so then you would just do some interpolation to find where it's actually at the correct CD or CL over CD value. Or, yeah, correct CL over CD value. Or rather, it's right here. Because zero lift would correspond to the negative 2 degrees. Roughly. And then you would just use your theoretical equations for the rest of this sort of thing. And then when you get down here, the local downwash, or rather right here, the downwash velocity is just the right over back in here is your induced angle in radians times the free stream velocity, and you would do that for each case. And that is how you would do this project.